The goal of this video is to understand and describe the forces and energies associated with springs. You probably already have an extensive experience and intuition with springs. The farther the spring is compressed, the more the spring pushes back, until it matches the force acting to compress it. The force that a spring exerts is directly proportional to the displacement of the spring. The constant of proportionality is written K and is called the spring constant or stiffness constant. It is dependent on the construction of the spring itself. This result is known as Hooke's law and is easily verified experimentally. It is important to note that the force the spring exerts is in the opposite direction of the displacement of the spring. If the spring is compressed, the force will be pointing in the direction to extend it. And if the spring is extended, the force will act in the direction to recompress it. A force that behaves in this manner is called a restoring force, because it acts to return an object to a stable equilibrium point. This force is a conservative force, although there may exist friction forces within the spring as it extends or compresses. Recalling the relationship between conservative forces and potential energy, we can quickly derive the potential energy associated with springs by integrating Hooke's law with respect to displacement. Because K is a constant, it can be pulled out of the integral, and the negative signs on either side of the equation will cancel each other out, leaving us with a change of potential energy equal to 1/2 kx sub b squared minus x sub a squared. Therefore, we can say that the term 1/2 kx squared is the potential energy that the mass spring system has at any given time, where x is the amount the spring is either compressed or extended. Since this displacement is squared, spring potential energy will always be positive. Consider a spring hanging vertically from the ceiling. We'll call the position at the end of the resting spring x equals 0. If we fasten a mass to the spring, the mass will experience a force of gravity acting downward. Since the spring has not yet been compressed, there is not yet any force from the spring. The net force is simply the force of gravity, so the block will accelerate downward, stretching the spring as it does so, until the spring is able to exert a force that balances the force of gravity. Because the net force acting on the block is 0 here, this is a point of equilibrium. If the block is pulled a little further down, the spring force will grow larger than the force of gravity, resulting in a net force upward, back toward the equilibrium point. And if the block is pressed upward against the spring, the force of gravity and the force from the spring will both act downward, resulting in a net force downward, again back toward the equilibrium point. If we press the block against the spring and then release it, we would naturally expect the block to accelerate downward. At the equilibrium point, the net force falls to 0, but the block has already obtained a velocity, so it will fall through the equilibrium point until the spring pulls it back, and this cycle will continue indefinitely in the absence of any friction or drag forces. By assigning a value to the spring constant, we can quickly sketch the displacement and velocity of one cycle of this oscillation. These shapes should make some intuitive sense. The displacement of the block from its equilibrium point starts at a maximum, falls through its natural resting place, and is then pulled back, following a cosine curve. The derivative of displacement is velocity, and the derivative of a cosine curve is the negative sine curve. Naturally, when the displacement of the block is 0, which is the block passing through equilibrium, the velocity of the block will be at an extreme. We can also sketch the energy that the block has as a function of time. The net work being performed on the block is equal to the net force on the block dotted with displacement, which is our change of potential energy. If we call the potential energy 0 at the point of the block's equilibrium, then the potential energy that the block has changes with the spring force. The spring potential energy is 1/2 kx squared, and the kinetic energy the block has is 1/2 mv squared. When the spring is at maximum displacement, the spring potential energy is maximum, and the kinetic energy is at a minimum. The dynamics of the problem can be more easily seen if we instead plot the energy as a function of position. Notice that the total energy, K plus U, remains always constant, and the potential energy graph visibly shows a point of stable equilibrium at x equals 0. We can use this idea to predict the compression of a spring upon a collision, which has many practical engineering applications. If a block is moving toward a spring in the absence of friction with some initial velocity, then we can safely say that the kinetic energy the block is starting with will be completely converted into spring potential energy when the block is at its maximum compression. Because the block starts with 25 joules of kinetic energy, we can solve the potential energy for delta X and plug in 25 joules for the total potential energy, which for a spring with a 1 Newton per millimeter stiffness constant corresponds to about 22 centimeters of compression.